All right, good morning. Hi, everybody. So as promised on Monday, I'm going to go through the answers to these structures. Hopefully you've had a chance to try them out. If not, you might want to pause or stop the video and give them a try on your own. As with all of this stuff in this class, it can make a lot of sense watching me do it, but then when you actually have to force yourself to do it yourself, it doesn't work out so well. So it's best if you can really try it and understand what you can and can't do yet, and then come back to me and work through it that way. All right. So that said, we're going to go through these 12 structures and then move on in the packet. So it starts pretty easy with just single atoms. Lewis dot structure or structural formulas for a single atom is just going to be that atom with its valence electrons distributed around it. So oxygen, we look up on the periodic table, has 6 valence electrons. We put those 6 around. As we said, we usually try to do them in pairs or in 8 so that we can see where the spaces are. But technically, you just need to have the dots around the atom. It doesn't matter how you distribute them. Okay, so now we have the oxide ion. The difference between an oxygen atom and an oxide ion is that the oxide ion is going to have a 2- charge, which means it has 2 more electrons. So instead of 6 electrons, we'll now have 8. And this should also kind of give you a visual as to why the oxide is the favored ion for oxygen, because this is the ion where all of the electrons are paired up and it has its 8 electrons. It has its full octet that makes it the most stable. All right, moving on, we'll just go down. Oxygen we did together, so I'm just going to draw that to have it in here. If you want to know how that one works, go back up to go to the last video where we went through that. Okay, nitrogen works in a similar way. I'm going to go through this one just to show you how to do it. So we're going to calculate the total valence electrons. Each nitrogen atom has 5, so 5 plus 5 equals 10. So that's 10 total valence electrons. Then we draw the structure and we start putting in those electrons. So we use 2 for the bond. So we got 4, 6, 8. So that electron's good, or that nitrogen's good, sorry. And then 10. And now we got a problem because we used up all our 10 electrons, but this nitrogen does not have 8 electrons yet, doesn't have its full octet. So we know now how to deal with that. That means that more electrons have to be shared. So instead of just one pair being shared between them, we can take one of these other ones and share that one. Check it again. This nitrogen has 8. This nitrogen has 2, 4, 6. So still not there yet. So then we can take another one and share those also. And now it works. 2, 4, 6, 8, 2, 4, 6, 8. So both nitrogens have their full octet. I know I'm going kind of quickly through these, so if you have a question or you want me to stop and go back over one of them, just let me know either in the chat or in Discord, and I'll go back over it. Okay, so over here we've got NH4 plus, so that's going to be 5 electrons from the nitrogen, 1 from each hydrogen, and there's 4 hydrogens, and then we've got to subtract 1 because of the positive charge here. So our total number of electrons is 5 plus 4 is 9 minus 1 is 8. So this one actually ends up working out quite nicely, where we don't have any non-bonding electrons to worry about. That's our 8 electrons. They're all used in those connections. So that's the entire structure. Because it's an ion, it's good to surround it with brackets and give it a positive charge. All right, H2CO. So we've got 1 electron from each hydrogen, and there's 2 of those. Then we've got 4 from the carbon and 6 from the oxygen, and that equals 12. So now when we build our structure, we have to think a little bit here. We know that hydrogen is listed first, but it can't be in the middle because hydrogen only can ever make 1 bond because it can only have 2 electrons. So there are a couple choices of how to distribute these. We can put the carbon in the middle and we can go O, H, H like that. we can put a hydrogen over on the other oxygen over here. That ends up causing some problems, but it would be still you can still make a working structure out of that, I think. So then we add our 12 electrons. So we've got 2, 4, 6, 8, 10, 12, and we run into that same problem where the oxygen's got its 4, the hydrogens have their 2s, but the carbon only has 6, so not enough electrons there. So we'll get rid of one of these non-bonding pairs on the oxygen, and we'll make it shared with the carbon instead. So we'll make that a double bond, and then that works. All right, moving up here, I think we did this one. Yeah, we did that one up there. So go back up there if you want to see how I went through that. PCl3, all right, so we got 5 electrons from the phosphorus, 7 from each chlorine, and there's 3 of them. So that's a lot of electrons, 26 total. Then we set up our structure. We've used 6 electrons, so we've got 20 more. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26. I think I counted that wrong. 2, 4, 6. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There we go. That one doesn't need any multiple bonds because we have enough electrons to get everything to the octets. All right, HCN, 1 electron from the hydrogen, 4 from the carbon, and 5 from the nitrogens gives us 10. This one we have to just kind of set up this way because the H can't be in the middle. So we'll assume it's just linear like that. And then we can start adding our electrons. So 2, 4, 6, 8, 10. Same issue. We don't have enough electrons here. So we have to share 2 pairs with the carbon so that the carbon can have its 8 electrons. The nitrogen can have its 8 electrons as well. All right, I'm going to leave the last 3 here for you. If you have questions, let me know. If you can't figure them out, these are common structures. You can look up the answers if you just want the answers. But if you have trouble getting to the answers, definitely let me know. I think you should be able to do these. And there's some more examples to work on there as well. Okay, so now we're going to talk about, we have to go back up here. I guess not. We're going to talk about something called polarity and electronegativity. And I think I'm missing a picture here. Okay, well, we'll find it. So there is a there's a quantity that elements have called electronegativity. See this here, which is a measure of how strongly that atom can attract electrons in a covalent bond. Right up there. How much does an atom attract electrons in a covalent bond? That's what the electronegativity answers. So as an example, if you have a bond like this, HH, there's no difference in those 2 atoms. So we would expect the 2 electrons in this bond to be shared equally. So if we imagine kind of like where those electrons would be, they're going to be evenly distributed around between those two atoms. And this is going to be true for any this is going to be true for any two identical atoms. So if you have like an oxygen molecule, same thing. You expect those electrons to be shared very evenly. But if you have two different atoms, the electrons are not shared evenly. So if you have, let's say, HCl, Cl has a higher electronegativity than hydrogen. And so what that means is these two electrons, instead of being distributed evenly around the two atoms, they kind of get pulled over to the chlorine side. So chlorine, being more electronegative, pulls those atoms or those electrons in the bond over. And what that does is it creates a polarity. Now, polarity means a separation of negative and positive. So if the electrons are being pulled more to one side, that means that one side is going to be more negative because it has more electrons, and the other side is going to end up more positive because it has fewer electrons. We're not talking about ions. It's not a full transfer of electrons the way like an ion actually gets more electrons. It's just like the electrons kind of spend more time over on one side than the other, and that leads to this separation of charge, this positive and negative area. So you can look these up. They're in the book. Let me see if I can grab the table that's supposed to be in the notes. I don't know if it's just not showing up on my computer or what. But it's in the linked section from on Blackboard. This is from our textbook. So here's a table of electronegativities. And the numbers might be pretty small in the video, but each element has an electronegativity, which is a measure of how strongly it pulls these electrons in the bond that we just talked about. So the most electronegative element is fluorine, way up here in the upper right, with a value of 4. And the least is francium, which is a radioactive element way down here that we're not really going to deal with. But it's important to know these because you don't usually need to look up the electronegativities on the table as long as you understand the overall trend. So if you know, for instance, that fluorine is the highest and francium is the lowest, then you know that anything that's kind of to the upper right of another element is going to be more electronegative. So if you have a bond between, let's say, carbon and oxygen, we can say, well, okay, maybe I don't know the exact values for the electronegativities of carbon and oxygen, but I know that oxygen is over to the right of carbon, and that means it's going to be more electronegative. So the oxygen is going to pull the electrons toward it away from the carbon. And we'll come back to this. So if we look at some different if we look at some different bonds here, we can predict which ones are going to be polar covalent and which ones are going to be non-polar covalent. So first of all, the easiest thing is that, as we said, any time you have two of the same atom, those are going to be non-polar. So no pen here. There we go. Sorry, everything's slowed down for a second. Okay, I think we're back. So you got anytime you see the same, FF, CL, CL, HH, always going to be non-polar. Similarly, we can think about the third category here, ionic bonds. We've already learned how to describe those or how to identify those by looking at metals and nonmetals. Those have such a huge difference in electronegativity that they tend to form ions instead of covalently bonding at all. So something like NAF is going to be ionic, and really that line, as we talked about last time, doesn't even make sense for that compound. And that leaves all of these other ones that have different atoms. And I can tell you that whenever you have two different atoms, it's likely that you're going to have a polar covalent bond. But there are some exceptions. When the difference in electronegativity is less than 0.5, that we say that that difference is so small that it doesn't really matter. And so if we looked up, let's say, a CH bond, right? H is 2.1, C is 2.5. So the difference between those two is 0.4. And so we say that that's nonpolar, even though there is a slight difference there. And I'm going to star that one because that's a really important bond. A lot of the compounds we're going to look at this semester use CH bonds, but it's important to know that they are nonpolar. And yes, Anna, that does mean that nonmetals are generally more electronegative than metals. Yes. So all of these other ones that we see here, HF, HCl, HO, CF, those are all going to be polar. And if you go back and look at the electronegativity chart, you can see that those differences are all greater than 0.4. So that helps us because it helps us predict intermolecular forces, which is something we're going to get into later. And it helps us predict whether an overall molecule is going to be polar or not. But in order to figure that out, we need one more step. And that is we need to know the shape of the molecule. Because as it turns out, if you have polarity going in opposite directions, so like the negative is pulled to the left and the negative is pulled to the right, those kind of cancel each other out. And so the overall molecule no longer shows that separation of positive and negative. So we're not going to go through a full treatment of how to do all of this. We're just going to do it part of the way. We're going to use this table here. And we're going to look at how many different electron groups, are called electron domains, are on a given atom. And we figure that out from the Lewis structure. So if we go back up to one of our Lewis structures here, let's just look at a couple of them. So NH4+, we would say we have 4 different electron groups around that central atom. 1, 2, 3, 4. And we're counting both bonds and non-bonding electrons, but only on the central atom there. If we look up at this one, we have 3 groups. 1, 2, 3. Notice I'm not counting the double bond as 2 groups, just 1. So we have 1, 2, 3 groups around that central atom. Let's look at one that has some electrons. So if we go up to this PCl3, if we look at the central atom here, we have, once again, 4 groups around the central atom. 1, 2, 3, 4. That lone pair, that non-bonding pair of electrons, counts as one of the electron groups. Excuse me. And then over here to the HCN, just 2 groups. 1, 2. So this comes from something called Vesper theory, which stands for valence shell electron pair repulsion. You can see that down here. And the idea is pretty simple. It's just that electrons are negative and they repel each other. And so anytime you have multiple groups of electrons attached to something, they're going to spread out so that they're as far away from each other as possible. And that predicts the molecular shape. So, for example, when we have 4 electron groups, well, let's start with 2. When we have 2 electron groups, the way that 2 groups of electrons can be furthest away from each other is to be on opposite sides of something, right? So that's where we get that 180-degree bond angle where one's here and one's here. And that's what we call linear. If we add a third group, the way that all 3 of those groups can be now furthest away from each other is to take the corners of a triangle. And that puts them at 120-degree angles, and that spreads them furthest apart. So it's not a T-shape like we've been drawing. It's more like a triangle, because a T-shape, you'd have 2 of those at 90-degree angles, which would not be as far apart. So if we make a triangle shape, what we call trigonal planar, they can be further apart. And then when we add a fourth electron group, we don't make a kind of a plus shape like this, because those would all be much closer. They'd be at 90-degree angles. To make them really spread apart, they can use all 3 dimensions because they don't have to be flat, the molecule's in space. And so if they use all 3 dimensions, we have this shape called tetrahedral. So you can imagine a shape with 4 equal faces, that, and 1 atom at each corner. That's called a tetrahedron. And so that shape is known as tetrahedral, and those bond angles are about 110 degrees. So we've got 180 degrees for a linear, 120-degree angle for a trigonal planar, and then about 110 for tetrahedral, which is way better than it would be if it was flat and had to be 90. Those would be closer together. So that's why we have this tetrahedral. So anytime you have 4 electron groups, like for example, in this NH4 structure, it's okay to express the Lewis structure as a flat plus sign like that. But the actual structure is going to be tetrahedral. So those hydrogens are going to spread out to make that shape. And if you look up in the textbook, there's some better pictures of that. You can also look up some videos on YouTube where you can see it rotating. When you come to lab, either today or next week, you can play with some models if you still have trouble kind of seeing that shape. That'll take that tetrahedral shape. And then if those atoms get replaced by electron pairs, like here, we still have a tetrahedral shape. So let's see if I can draw this. Always hard to draw these things in 3 dimensions. So what this would look like is we'd have the P in the center. And then the CLs would kind of be around like this. And sometimes the symbols we use is a wedge shape to show that it's coming out at you. And then a dash shape to show that it's kind of going back behind that way. So you have this kind of pyramid shape. And then the lone pair, or the non-bonding electrons, kind of take up the extra space on top. That's our tetrahedral shape. Now here's where we start differentiating between connected atoms and non-bonding electrons. The electrons take up space in these in this Vesper theory. They take up a spot, but in the actual molecule, we can't see them. So they don't actually like come up and are on a stick like that. They're just hanging around on that atom. So the actual shape of that molecule is not quite tetrahedral. The angles are tetrahedral, and the basic shape comes from tetrahedral, but the true shape is this pyramid shape, which is called trigonal pyramidal. So there's an example down here in the table again. And that's what the right side of this table is showing you. You can have 2, 3, or 4 total electron groups, including bonds and non-bonding electrons. And that gives you that overall geometry. There you have 3 choices: linear, trigonal, planar, or tetrahedral. There are more, but we're not going to deal with them in this class. And then if there are lone pairs, which are pairs of non-bonding electrons, they take up a space, and so the actual shape of that molecule becomes a little bit different. It becomes either bent or a trigonal pyramidal, depending on how many spots are taken up. So then when we know those shapes, now we can start thinking about the overall polarity of the molecule. And this can get really tricky. We're not going to get into the full treatment of this in this class. But let's take a look at kind of how we would evaluate one. So we'll stick with our PCl3, which we just have been looking at. And we can draw the Lewis structure like this, even though we know now that that's not really the true 3-dimensional structure. It's okay to draw a Lewis structure with just regular 90-degree flat angles. So there's our structure. And then we're going to answer some questions about it. How many electron groups does the central atom in the molecule have? So we look back up at our Lewis structure, and our total electron groups are 1, 2, 3, 4. So 4 electron groups. Oh, wait, there's a spot for this. Sorry. So 4 total electron groups, 1 lone pair of electrons, so 1 non-bonding pair of electrons. So now we can look at the table and say, all right, well, if we have 4 groups and 1 lone pair, what kind of shape would we have? 4 groups, 1 lone pair. That's going to give us trigonal pyramidal geometry. So our electron geometry is tetrahedral. That means including everything. Our molecular shape is trigonal pyramidal because now we're not including that lone pair of electrons. So electron geometry is bonds and non-bonding electrons. Molecular shape is what happens when we just look at the atoms and how the atoms are connected. All right, so that's shapes. So I think the last thing we're going to do here, well, we'll see. We'll see if we can get to the other thing or not. Larger molecules, particularly organic molecules. So, what if you had something like this? Some big giant structure with a whole bunch of atoms. Then what we talked about with Lewis structures doesn't quite work because you'd come up with, I don't know, 50 some electrons, and then you're trying to connect it, and there's now like many different combinations and ways to connect things. So it just doesn't really work. The techniques that we've used only work for small molecules, very small molecules. When we get to bigger molecules, we have to make some assumptions that usually work out. And some of these patterns we talked about last time you may have noticed. Like carbon usually has 4 bonds with no lone pairs. Nitrogen usually has 3 bonds with 1 lone pair. There are some exceptions, like in NH4 plus ammonium. Hydrogen usually has 1 bond with no lone pairs, and oxygen usually has 2 bonds with 2 lone pairs. Again, there's exceptions, that's why it says usually. But for bigger molecules, we can take these usuallys and just say, well, okay, I've got to assume this because it's the only chance I have. So we can look at a big structure like this. And the question is here, there are 3 hydrogens and 5 lone pairs missing. Draw them in. So how do I do that on a big molecule like this? I have to look at the atoms and I have to decide which of these atoms have things missing. And the only way I can really do that is by making these assumptions that we just talked about. So if I assume that carbon always makes 4 bonds, which is a pretty good assumption, almost always does, then I can look at my carbons and say anything without 4 bonds needs something else. So 1, 2, 3, 4, that one's good. 1, 2, 3, 4, that one's good. 1, 2, 3, 4, that one's good. 1, 2, 3, uh-oh, this one's missing something. So I'm going to put an extra hydrogen there. 1, 2, 3, that looks like it's missing something too. Extra hydrogen. 1, 2, 3, that one's missing too. Another hydrogen. This one's got 4. This one's got 4. That one's just 2. So, or that's oxygen. Never mind. We'll get to that later. So we found a couple missing hydrogens there. All right. Now 5 lone pairs. Well, what types of atoms usually have lone pairs? Oxygen and nitrogen. Nitrogen usually has 1. Oxygen usually has 2. So we can look at the nitrogen here and say, okay, well, that lone pair is going to be here. And then these oxygens should have 2 as well. So that's how we can help deal with some of these bigger structures. And then we can also use these assumptions to build bigger structures. So for example, let's look at something like CH5N. Now we could do this the old way. We could, count up all the electrons and do all of that. Or we can take a little bit of a shortcut and say, look, I know carbon's going to have 4 bonds, and I'm pretty sure nitrogen's going to have 3. So let's just start from there. We'll put the C and the N together. We'll add 3 hydrogens to the carbon. And then we've got 2 more hydrogens for the nitrogen. We can add those as well, and a lone pair. right? So, if something weird happened here and you didn't have enough atoms, that's when we start having to look at, all right, how many electrons are there? Do I have to make multiple bonds? Whatever. But with these assumptions, we can more quickly design our structures. And so for these other ones, the shell or the basic structure is already given to you. All you have to do is fill in multiple bonds and lone pairs. So you can see if you can do that. All right, I have to stop here because I have to get ready to get to campus and get lab ready. But I would like to get into the polarity stuff a little bit more. So I think what I'll do is I'll have to come back on tomorrow morning to finish this up and talk about polarity of molecules. So I have another class at 9:30 tomorrow morning. So I'll do this just before at 9, and then I'll do the class at 9:30. So thanks, everybody. I will see half of you at noon. Make sure that you are cleared for campus. If you're in Group B, but you would like to come and get your exam today, just pick it up. As long as you're cleared for campus, you can come stop by lab, and I'll give you your exam. Otherwise, I'll have them for you next week. All right, thanks. See you later.